If the machine is connected to a 240 volts power supply, the current or amps will decrease compared to the same machine connected to a 208 volts power supply. According to Ohm's law, the current represented as I in an electrical circuit is directly proportional to the voltage represented as V and inversely proportional to the resistance represented as R. The formula is I equals V divided by R. In the case of an electric pressure washer, the motor and other components have a fixed resistance. When the voltage is increased from 208 volts to 240 volts, the current will decrease because the resistance remains constant. Mathematically, we can express the change in current as delta I equals voltage 2 minus voltage 1 divided by R. Delta I is the change in current. Thone is the initial voltage of 208 volts. V2 is the new voltage of 240 volts. R is the fixed resistance of the motor and components. Substituting the values, we get delta I equals 240 volts minus 208 volts divided by R, which then simplifies to delta I equals 32 volts divided by R. It's important to note that since delta I is positive, it means that current will increase when voltage is increased. If the electric pressure washer is connected to a 240 volts power supply, the current draw will decrease compared to the same machine connected to a 208 volts power supply. This is because the increased voltage will cause the current to decrease in order to maintain the same power output. Ohm's law is a fundamental principle in electrical engineering and provides a clear relationship between voltage, current, and resistance in an electrical circuit. Understanding how these three factors interact is crucial for analyzing and designing electrical systems. Let's delve deeper into the concepts to provide a more comprehensive understanding. Voltage, also known as electrical potential difference, is the driving force that pushes electric charge through a circuit. It is measured in volts. Think of it as the pressure in a water pipe that causes water to flow. The higher the voltage, the more pressure there is to push the current through the circuit. Current is the flow of electric charge through a circuit. It is measured in amperes or amps. It is the rate at which electric charge flows past a point in the circuit. Think of it as the amount of water flowing through a pipe. The higher the current, the more charge is flowing per unit of time. Resistance is the opposition to the flow of electric charge in the circuit. It is measured in ohms. Think of it as the narrowness of a water pipe that restricts the flow of water. The higher the resistance, the more difficult it is for the current to flow. Now let's revisit Ohm's law I equals V divided by R. This equation tells us that the current in a circuit is directly proportional to the voltage and inversely proportional to the resistance. Directly proportional means that if you increase the voltage, the current will increase proportionally, assuming the resistance remains constant. Inversely proportional means that if you increase the resistance, the current will decrease proportionally, assuming the voltage remains constant. In the context of the electric pressure washer example, the resistance of the motor and other components is assumed to be fixed. When the voltage is increased from 208 volts to 240 volts, the current will decrease because the resistance remains constant. The power delivered to the pressure washer is given by the formula P equals V times I, where P is the power in watts, V is the voltage in volts, and I is the current in amps. If the power remains constant, then increasing the voltage must result in a decrease in current. Let's consider a numerical example to illustrate this concept. Suppose the electric pressure washer has a resistance of 10 ohms. When connected to a 208 volts power supply, the current would be I equals 208 volts divided by 10 ohms, which equals 20.8 amps. The power delivered to the pressure washer would be P equals 208 volts times 20.8 amps, which equals 4,326.4 watts. Now let's connect the same pressure washer to a 240 volts power supply. Since the resistance remains constant at 10 ohms, the current would be I equals 240 volts divided by 10 ohms, which equals 24 amps. The power delivered to the pressure washer would be P equals 240 volts times 24 amps, which equals 5,760 watts. However, this would result in an increase in power, which may not be desirable or safe for the pressure washer. To maintain the same power output of 4326.4 watts, the current must decrease. To find the current required to maintain the same power output, we can rearrange the power formula to solve for I equals P divided by V. In this case, I equals 4326.4 watts divided by 240 volts, which equals 18.26 amps. Therefore, when the electric pressure washer is connected to a 240 volts power supply, the current draw will decrease to approximately 18.26 amps in order to maintain the same power output of 4326.4 watts. It is important to note that this analysis assumes that the resistance of the motor and other components remains constant. In reality, the resistance may vary slightly with changes in temperature and other factors. However, the general principle remains the same. Increasing the voltage will generally result in a decrease in current, assuming the resistance remains relatively constant and the power output is to be maintained. In summary, Ohm's law provides a fundamental understanding of the relationship between voltage, current, and resistance in an electrical circuit. By applying this law, we can analyze and predict how changes in voltage will affect the current in a circuit, such as the electric pressure washer example. This knowledge is essential for designing and operating electrical systems safely and efficiently. When dealing with electrical systems, it's crucial to consider safety precautions. Firstly, always disconnect power before working on any electrical equipment. This prevents accidental electric shock. Secondly, use properly insulated tools and equipment. This ensures that you are protected from coming into contact with live electrical conductors. Thirdly, follow all applicable electrical codes and regulations. These codes are designed to ensure the safe installation and operation of electrical systems. Fourthly, if you are not comfortable working with electricity, consult a qualified electrician. The electricity can be dangerous, and it's best to leave complex or hazardous tasks to professionals. Moreover, be aware of the voltage and current levels you are working with. High voltages can be lethal, and even low voltages can cause painful shocks. Be especially cautious when working with wet or damp conditions, as water can significantly increase the risk of electric shock. Always inspect electrical cords and equipment for damage before use. Frayed or damaged cords can expose live wires and create a shock hazard. Replace any damaged cords or equipment immediately. When using extension cords, choose the appropriate gauge for the intended use. Using a cord that is too small can cause overheating and create a fire hazard. Avoid overloading electrical circuits. Plugging too many devices into a single circuit can cause the circuit breaker to trip or even start a fire. Distribute the load across multiple circuits if necessary. Be mindful of the presence of flammable materials when working with electricity. Sparks from electrical equipment can ignite flammable materials and cause a fire. Keep flammable materials away from electrical equipment and work areas. If you are working on a circuit breaker panel, be sure to identify the correct breaker before turning it off. Labeling the breakers clearly can prevent accidental power outages to other parts of the building. When working with electricity, it is always better to be safe than sorry. Take the time to understand the risks involved and follow proper safety procedures. If you have any doubts or concerns, consult a qualified electrician. Now let's shift our focus to the impact of voltage and current on motor performance. Electrical motors are designed to operate within specific voltage and current ranges. Operating a motor outside of these ranges can lead to reduced performance, overheating, and even premature failure. Firstly, undervoltage occurs when the voltage supplied to the motor is lower than the rated voltage. This can cause the motor to draw more current in an attempt to maintain its output power. The increased current can lead to overheating and damage to the motor windings. Secondly, overvoltage occurs when the voltage supplied to the motor is higher than the rated voltage. This can cause the motor to run faster than its design speed, which can damage the motor and the equipment it is driving. Overvoltage can also lead to insulation breakdown and premature failure of the motor windings. Thirdly, overcurrent occurs when the current drawn by the motor exceeds its rated current. This can be caused by various factors, such as overloading the motor, low voltage, or a fault in the motor windings. Overcurrent can cause the motor to overheat and damage the windings. Fourthly, voltage imbalance occurs when the voltages in a three-phase power system are not equal. This can cause unbalanced currents to flow in the motor windings, leading to overheating and reduced performance. Voltage imbalance can also damage the motor windings over time. To protect motors from these issues, various protection devices are used. Firstly, circuit breakers are used to protect against overcurrent. They trip and interrupt the circuit when the current exceeds a predetermined level. Secondly, fuses are also used to protect against overcurrent. They melt and break the circuit when the current exceeds a predetermined level. Thirdly, overload relays are used to protect against motor overheating. They monitor the motor current and trip if the current exceeds a safe level for a prolonged period. Fourthly, voltage monitors are used to protect against undervoltage, overvoltage, and voltage imbalance. They monitor the voltage and trip if it falls outside of a safe range. In addition to these protection devices, it is important to properly size the motor for the intended application. Using a motor that is too small can lead to overloading and premature failure. Using a motor that is too large can be inefficient and waste energy. Regular maintenance is also essential for ensuring the reliable operation of electrical motors. This includes inspecting the motor for damage, cleaning the motor to remove dirt and debris, and lubricating the motor bearings. By understanding the impact of voltage and current on motor performance and implementing appropriate protection measures, you can ensure the safe and reliable operation of electrical motors. Now let's explore the National Electrical Code, or NEC, and its relevance to electrical installations. The NEC is a comprehensive set of standards and guidelines for the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years to reflect the latest advancements in technology and safety practices. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is essential for electricians, engineers, and anyone involved in electrical work to be familiar with the NEC. Firstly, Chapter 1 of the NEC covers general requirements such as definitions, wiring methods, and equipment installation. Secondly, Chapter 2 of the NEC covers wiring and protection, including overcurrent protection, grounding, and surge protection. Thirdly, Chapter 3 of the NEC covers wiring methods and materials, including conductors, cables, and raceways. Fourthly, Chapter 4 of the NEC covers equipment for general use, including receptacles, switches, and lighting fixtures. Fifthly, Chapter 5 of the NEC covers special occupancies, such as hazardous locations, healthcare facilities, and swimming pools. Sixthly, Chapter 6 of the NEC covers special equipment, such as electric signs, elevators, and electric vehicles. Seventhly, Chapter 7 of the NEC covers special conditions, such as emergency systems, fire alarm systems, and communications systems. Eighthly, Chapter 8 of the NEC covers communications systems, such as telephone, data, and CAT-EV systems. Ninthly, Chapter 9 of the NEC contains tables and examples to aid in the application of the code. Some specific NEC articles that are relevant to the electric pressure washer example include Article 210.8, which covers ground fault circuit interrupter or GFCI protection for personnel. This article requires GFCI protection for receptacles installed in certain locations such as bathrooms, kitchens, and outdoors. Article 430 covers motors, motor circuits, and controllers. This article provides requirements for motor overcurrent protection, motor disconnecting means, and motor control circuits. Article 680 covers swimming pools, fountains, and similar installations. This article provides requirements for bonding, grounding, and GFCI protection in these locations. It is important to consult the latest edition of the NEC for the most up-to-date requirements. The NEC is available for purchase from various sources such as the National Fire Protection Association, or NFPA, and bookstores. In addition to the NEC, many states and local jurisdictions have their own electrical codes. These codes may be based on the NEC, but they may also have additional requirements that are specific to the local area. It is important to be familiar with the electrical codes that are in effect in the area where you are working. To ensure compliance with the NEC and local electrical codes, it is important to have your electrical work inspected by a qualified electrical inspector. Electrical inspectors are trained to identify potential hazards and ensure that electrical installations meet the required safety standards. Obtaining an electrical permit is typically required before starting any electrical work. The permit process involves submitting plans for the electrical installation to the local building department for review and approval. The building department will then schedule an inspection of the electrical work to ensure that it meets the requirements of the NEC and local electrical codes. Compliance with the NEC and local electrical codes is essential for ensuring the safety of electrical installations. Failure to comply with these codes can result in fines, penalties, and even legal action. Moreover, non-compliance can create a safety hazard that puts people and property at risk. By following the NEC and local electrical codes, you can help to ensure that electrical installations are safe and reliable.